My name is Jim Kelleher. I'm the general manager of Seneca Balance in Maryland. I have been in the tab industry, testing industry, commissioning, installation, and various things for the last 28 years. And an interesting opportunity came up in the DC market for me to do some special inspector testing. And we're going to dig into a little bit what that means, but the fun side of it was I got to play with some smoke generation in a big environment. And then that led to playing with more smoke and more environments and more. So it was a lot of fun, smoke in a building. And I thought it would be neat to put a presentation together to just briefly touch on the different types of smoke visualization testing that I accomplished for the Washington, D.C. Inspector, and just one location. I'm not going to spend a whole hour going through, look at this smoke, look at that smoke. In actuality, it's just about the last 20 minutes or so of the presentation where we'll actually see some video, picture, and that sort of things. What I do want to emphasize highly, though, is the importance that all of us play in the life safety environment. And you'll notice that that's a big portion of what our discussions are today, including history and background. It's not going to be a true history session where I just, boringly read on and on about all the people that have paid the ultimate price so that we can design buildings better. But it's an injustice to those who have passed in a building issue, who paid that ultimate price so we can learn to be better, to not recognize that, remind ourselves what happened, and let's try not to let these sacrifices have to keep on going. So we take pride in our work. Life safety systems have the utmost critical attention to detail, and that's something we're going to dive into. We'll talk a little bit about some of these things coming up. So the title, Method of Visualization Testing for Hotel Smoke Removal Systems, and it is approved for credits. The presentation, we're going to illustrate methods of conducting smoke removal. It's in a hotel environment, and we're going to cover three categories of smoke control. We're going to look at an atrium, which would be our large volume exhausting type system. We're going to look at a ballroom, which is a smaller volume, and we're going to look at corridor testing. And we're going to discuss the different methods that we were able to accomplish a challenged environment for the designer of record and the authority having jurisdiction and the owner to sign off on their confidence levels that the systems will work. As you'll see, it's a big facility that we did. I'm only showing you one example of each of these tests, but in a broader scheme of things, you can probably imagine how big the Dog and Pony Show was. It was pretty extensive, and we'll dig into that in a little bit. So we're going to review the actual field performance, explore smoke generating equipment, the effects on field of view, and the factors that help us decide which was the right solution for each scenario that the AHJ, DOR, and owners reps wanted to challenge. At the end of the course, the participants will be able to understand the varying types of smoke evacuation systems as they relate to architectural factors. We're going to briefly dip into the International Building Code. We're going to understand the benefit of thermally assisted smoke plume generation for high ceiling environment. When you test a 16-story open atrium, you got to get the smoke up to the reserve level. So we're going to talk about how we made that happen. We're going to talk about use, control, and limitations of theatrical fog generations in field performance testing and how we were able to utilize a glycol-based fog, theatrical fog. If any of you are weekend DJs, it's the same thing you're using when you're doing your weekend work. We're going to discuss the benefits of the varying type of smoke generation and a comparison of smoke versus fog, what we liked or didn't like about the two different products as far as controllability. So historically speaking, we get better with time. Unfortunately, every time we think we're better, we get proven again that we're not. And we got to get better and better and better. And that's what we're working on. So we're going to talk about 4 different events that were remarkable in various ways for our discussion today. We're going to talk a little bit about the smoke control, background of smoke control, how the International Building Code directs us in the direction of installation verification, acceptance testing. We're going to talk a little bit about special inspector conditions and how all of those of you in the room should already know these requirements in Chapter 17 of the International Building Code, but if not, it's definitely a good homework assignment. You can improve your revenue generating streams if you pursue the avenue of working with your local authority, having jurisdiction, and get yourself on their approved list as a special inspector for those jurisdictions that have that, or work with general contractors who are in the new building construction process and help get on their team as a special inspector. We're going to, of course, then jump into the case study. We're going to call it the hotel. And during that, we'll be talking about atrium design concepts, special test equipment, and the smoke demonstrations. This is the MGM Grand Hotel and Casino. The left picture is the casino. The right picture is someone being helivac'd off of a balcony. This is not the type of marketing that helps anyone in our industry, fire protection, or building owners. These are the types of things that we don't want to have happen. The MGM Grand fire at the time was, it may still be, one of the worst disasters in Vegas, in Nevada's history. There were about 5,000 people in the MGM at the time of the fire. And this hotel is a casino and 26-story hotel with 2,000 rooms. And within minutes, firefighters arrived on the scene. They estimated the fire started a couple minutes after 7 a.m. and within 15 minutes, because there was a fire truck across the road, they had firefighters on site. You would think, my gosh, you can't get any better response time than that, right? Yet still somehow 85 people perished. So what happened here? We had an electrical fault in the wall receptacle that caused the fire. This wasn't user abuse. This wasn't too many things plugged in. This wasn't faulty equipment. It was a bad electrical connection that finally vibrated to the point of shorting and causing a fire. The fire spread to the lobby, 15 to 19 feet per second, estimated. About 6 minutes to engulf the casino, which had no sprinkler system in place because they didn't need it then. That wasn't a requirement. Panic ensued throughout the building. Part of that was due to the fact that the smoke and fire was allowed to rise up through the stairwells. The smoke did. Stairwells, seismic joints, and elevator banks. The fire itself was limited to the first floor. But as we know, smoke is toxic, and it's scary, and it causes people to get confused, disorientated, and or pass out until they're overcome and pass. The stairwells, the stairwell doors were predominantly propped open by tenants, because why do we need automatic closure doors when I just want to get up and down from my floor to the next floor, and these locking doors are a pain in the butt, right? We had faulty smoke dampers that allowed circulation of toxic gases. We had continued operation of ventilation systems, which should have shut down to help isolate. And remember the time frame, 1980, right? So the hotel telephone switchboard area was overcome. They couldn't call the rooms to evacuate everybody. They didn't have a central system digitalized like we do now. They had to make calls. They couldn't get everyone out. 5,000 guests were present, 85 perished. So we had a lack of smoke control, we had egress issues, and we had no sprinklers on the casino floor. A lot of lessons to be learned there, and a lot of reasons why we see code development over the years when issues like this happen. The Meridian Hotel, 1991. This is in Philadelphia. And we have some minor construction going on, which has resulted in smoke control systems being disabled. and part of the renovation included some refinishing of some wood products. And we find that a pile of linseed oil-soaked rags combusted, started the fire. The incomplete smoke detector system allowed it to grow and conflagrate. Firefighters were hampered in a number of ways. There was no smoke removal in the stairwell. They couldn't safely get up to where the fire was because they couldn't see where they were going. And they had loss of fire main pressure. This is a tragic one here. They had a fire hose stack, fire supply stack, with automatic regulating valves set for 65 to 100 psi by design, but it was never commissioned. They didn't work. They weren't installed right. They weren't adjusted right. So when the firefighters went in to attach to and fight the fire, they had no water pressure. Then they got confused and disorientated because the smoke evac system wasn't available to them. They couldn't get the smoke out. 3 firefighters were sent to go open up the stairwell shaft to the roof to try to alleviate the smoke. Those 3 firefighters perished. So something that we can do in commissioning and our services provided if we're in this line of work, regulating valves, right? Now look at the level of testing that we do on fire pressurized sprinkler systems and such. It's starting to come around, right? We're starting to see how we can learn from the losses of others and get better at what we do. And then lack of ventilation and smoke removal, which affected, if it had been occupied in that area, it would have affected egress, evacuation. Unfortunately, it affected the accessibility for the firefighters to go attack the fire. 3 firefighters perished, lack of effective smoke control and egress, low fire water main pressure, poor smoke detector coverage, and housekeeping during construction. So now we think in our present day environment, look at all the things that we do because other people have paid the price. Monte Carlo, here's a success story. Imagine driving down the Las Vegas Strip and you look up and you see fire on the roof. That's what happened. That's how fire was turned in. Somebody drove by and saw it. There was a welder up there on the roof. He didn't protect his work area properly. Slag caused a fire, but they had an interesting concept. So we're in later developments of systems and buildings, and there's more compartmentation in design concepts. And in this case, there was a gypsum layer providing isolation from the exterior to the interior that helped keep the fire under control and kept it outside of the occupied environment. As a matter of fact, the firefighters didn't fight from outside. They actually went into the upper floors, busted out windows, and they were able to get their fire hoses by hanging out the windows and put the fire out. The fire was contained and the people were evacuated. There was enough time allowed because of compartmentation. It's a vital concept when you are looking at fire control systems, following the egress point from where people are to where they need to go, and how are the compartmentation aspects maintained. And a lot of that has to do with our systems, pressurization and evacuation systems. The layer of gypsum between the exterior and interior wall provided enough of a barrier to allow the slow spread. And it's a testament to good firefighting response and barrier containment. All right, this one's really bad. And that's the last one we're going to cover before we start talking about some other aspects here. But I want to talk about this particular, it's a residential, it's mixed-use residential. It's in London, and it's going to shock everybody to hear how this happened, but they had a stay-in-place policy. I mean, I don't know how many times we have to study the history of the Titanic to know ships sink, buildings burn, right? These designers and operators, owners convinced themselves that they built such a well-constructed, safety-conscious building that the safest place for its residents to go in the event of a fire is to stay in place and lock down. Unfortunately, that was tragic. 1 a.m. a fire breaks out in a residential unit. By 3 a.m. the building was fully engulfed. The tower had a stay put policy, believing the design compartmentation would prevail. Smoke engulfed all the exit routes. When they decided to evacuate the building, they had no way to get people out. Within 26 minutes, their decision to have a stay put policy had failed, and they couldn't get the people out by that time. 72 people perished. So, got a whole lot of issues going on here, and we're all a part of it in our everyday work. We're in the testing industry, we're in the verification industry, and many of you are in the design industry. Whether you deal directly with fire systems or indirectly with fire systems, what we do matters, and what we learn and what we know can help the next project get better. And that's the importance behind fire and life safety, and some of the reasons why an owner who might be told, well, smoke visualization testing, it just doesn't do anything for you. The smoke's not the right density, we don't have the right temperature, we're acting like this is where the fire is going to be. We don't know where the fire is going to be. Well, it just gives another level of comfort to a design and a design team and an authority having jurisdiction that things have been done well enough that if we challenge it with a significant simulation, we can look at, see, and hopefully approve the results of the operation. So what did we learn from these examples? A myriad of things: housekeeping, fire suppression systems, containment, isolation features of construction, design and operational, evacuation, egress routes, plan and practice, and protect the firefighters by smoke evacuation and firefighting resources such as the water main. So by a combination of all these factors, what's our number one goal of a building fire safety system? Number one goal, to get the people out, right? Number two goal, get the fire out if you can to protect it from catching the next building over. Rarely is the goal to save the structure. I mean, yes, that's good because a structure that is completely engulfed is likely to cause other damages and such, but get the people out, right? So smoke control systems are designed and built to provide egress opportunities during an event. Some facts about smoke, because that's the real killer in a fire, is the smoke. It's toxic. 75% of all fire deaths or deaths associated by a fire in a building are by smoke inhalation. Over half of the deaths occur outside of the origin of the fire, like we saw in the casino fire, right? All those lives were lost, but it wasn't in where the fire was in the casino floor. Over half of the fire deaths outside the area. It was surveyed survivors of fire events. Half the survivors said they couldn't see more than 12 feet as they evacuated in many cases. And smoke travels quickly, 120 to 240 feet per minute. So what are our key aspects of smoke control with these factors considered? Well, we want to inhibit the migration of smoke to the stairwells, areas of refuge, elevator shafts, and similar areas, right? What good is it to have an egress route if your egress route is compromised, right? We want to maintain a tenable environment in those areas of refuge and during the time it takes to evacuate. And then we want to facilitate fire and rescue by improving visibility. If we can get the smoke out, they can get in, they can put the fire out, they can search for incapacitated people, survivors, get them out. If they can't get in, whoever's left is going to pass. They're going to perish. Protect life and reduce damage to property. So, some of the factors affecting smoke management. When we look at a room like this, right, we got a high ceiling, it's nice, it's airy, it's easy to get comfortable with a lot of people in here because the reserve capacity is built into all this air. Well, some of that is a very strong factor in the design of smoke control systems too in large area environments, malls, atriums, things like that. Some of the factors are the buoyancy of the combustion gases. It's less dense, tends to rise, right? HVAC operation, we can either use it or isolate it. And in many factors, you'll see both. So now your HVAC systems become part of the fire protection system because they don't shut down. They just configure the smoke dampers to operate in conjunction with fire dampers and use them for egress or egress control and or pressurization schemes, positive or negative, depending on whether you're talking about maintaining an egress route smoke clear or whether you're talking about clearing smoke from an area. Natural convection, of course, the circulation due to the heat of a fire event. There's a lot of talk about why smoke visualization studies are not an effective means of challenging a system because you don't have the heat. How can you just inject cold smoke into an area and act in any way like that's going to simulate a condition in a building that's realistic? It's not. So you either have to keep that in mind and take into account that you're just looking for draft control, pressure control, and general flow of the smoke, or you have to try to simulate that heat factor in your testing methods. And we're going to see two examples of that. Thermal expansion, the heat of expansion of the gases, must be relieved by the smoke control. Eventually, a space will be overcome with the heat of expansion of the gases, pushing down, stay low in a fire, right? Pushing down and taking over the people area, the occupied area. I was in the Navy, I was on submarines, right? And so we had two rules there: keep the water out of the people tank, keep the smoke out of the people tank, right? So it's kind of easy to relate that to our industry when we're talking about egress and design concepts. Keep the smoke out of the people tank, whether that be the stairwell, the egress route. Stack effect. Stack effect is an interesting phenomenon that bears its own discussion. It's not going to happen today, but stack effect is an important factor to consider. Those differences in air pressure from inside to outside of a building structure based solely on the temperature differential from inside to outside, knowing that if you're in certain climate areas, it absolutely reverses summer to winter. In other areas, it's not so dramatic. But it can be a very large factor in the design concepts. Always factored in stairwell construction, because if you're doing a 10 to 30 story building stairwell system, you're going to have stack effect in that amount of vertical rise in a building. So we get to smoke management systems, and now we talk holistically, what are we trying to accomplish with them? So to modify, dilute, to redirect, right? Anything to get it out of the people's egress routes. It's intended to limit and control the movement, to buy time. That's all we're trying to do in a fire event, right? Buy time. Why do we have large landings and stairwells? To buy time for somebody who's in a wheelchair and can't go down the stairs. They are benefiting from your stair pressurization test by having those extra minutes of sitting there waiting for someone to come rescue them, right? It's all about buying time to get the people out. Compartmentation, use of barriers, fire and smoke to isolate fire from other areas. So when you go on a tenant improvement project and you look above the ceiling and there's all these gaping holes through a smoke wall on a corridor, you know that's not right. People aren't understanding when they're outside of the original construction process what's good and what's not good, what's allowed, what's not allowed. I don't know if y'all are aware of it, the new 2021 building code, IBC, states that above ceiling markings have to be applied on walls that are used as barriers, smoke or fire. So the most common examples are mechanically induced pressurization schemes, airflow design, and exhaust ventilation. Those are the three that we're going to run into with our smoke control systems. We're either going to pressurize it out, we're going to dilute it, or we're going to ventilate it. Chapter 9 of the International Building Code is where a lot of our activities are originating, in the smoke control system section 909. Pressurization method in point 6 tells us that we have to maintain a 0.05 barrier That's where that number comes from when we're seeing it on our drawings and in the practice of doing our testing. An airflow design method is 200 feet per minute upper limit. So if the concept is for a smoke control door or other door to open, and you don't want to feed the fire, the airflow offset is now no longer a pressure offset because you just created an open area. Now it's a 200 feet per minute limit. And an exhaust method is designed to keep smoke above or reduce the smoke volume sufficiently to maintain a 6-foot exit pathway. Acceptance testing is the section that we all need to take aware of and make sure that when we're doing testing on a project, these particular aspects are picked up upon by the engineer in his notes, because we can't always just show up going, well, I did what the drawing said, right? We have to be above that to the point of knowing when it's incomplete so that we can at least ask the question. And if the answer is shut up and do what you're told, then you do what you're told and make a note in your report. That doesn't usually happen anymore in our industry, but a lot of people say to me, well, why do you concern yourself so much with what the design engineer is supposed to know and supposed to implement? Because who's checking him? We are. I mean, it's our business, it's our trade. This is how we make a living. So if we take a few minutes and read some of these sections of the International Building Code, we'll know what he's looking at. We'll have a better understanding of why a system's supposed to do what it's supposed to do. Acceptance testing is a provision of this code. So now we know we have to do acceptance testing if it has smoke control. And later on, we're going to see who's allowed to do acceptance testing. And tab doesn't always include acceptance testing, although you'll see in a minute here, I think it's 7 out of the 9 items required are right in your tab report if you're doing tab. Or if you're doing commissioning verification, you're going to see it's all right there in your work. The commissioning effort will include an in-depth fire life safety testing and acceptance testing with specialists, but they will still need tab support. And then understand what your code officials and designer of record require. And I always encourage people, always put your report in ahead of time. If you're going to do a smoke control test or if you're going to do a stairwell test, get your report parameters submitted so that you have a little better control of helping everyone understand where your interpretation of the requirements come from. Now here are the 9 parameters of the acceptance testing. Detection devices, testing and verification, not typically included in anybody's scope of work on the plan, inspect, test and balance level. That would normally be in the commissioning of the fire life safety systems. However, dot 2, ducts traversed for air quantities. Dot 3, dampers functional testing. Dot 4, inlets and outlets measure airflows. Dot 5, fans. Dot 6, pressure differentials. Dot 7, sequences testing. And then dot 8 is who can do it. And then dot 9 is identification and documentation. So right there in the acceptance testing, in the building code that everybody has to follow, there's our scope of work. Guys, this is our work. Smoke control systems shall be tested by a special inspector. So we're going to have to get into that and find out who that is. So Chapter 17 of the Building Code talks about special tests and inspections. Smoke control systems shall be tested by a special inspector. The scope shall include, look at that, leakage testing of ductwork and recording of device locations. So they kind of group it together, but no one's doing duct testing but us, right? We're either commissioning it or we're performing it. Prior to occupancy and after sufficient completion for the purposes of pressure differential, flow measurements, and detection and control verification. Again, we're there. We just don't know why we're there because we're doing it because it's in our scope, it's on the drawings. This is why we're there. Approved agencies for smoke control testing shall have expertise in fire protection engineering, mechanical engineering, and certification as air balancers. So that's an interesting concept. You must be certified as an air balancer but you only have to have knowledge and expertise in fire protection engineering, mechanical engineering. So there you have it. And then in special inspector qualifications, the registered design professional in charge, engineer of record, are permitted to act as the approved agency, provided they also qualify as special inspector. So all the design engineers also have to be air balancers. Clearly, these efforts get combined, right? So a general contractor and architect are working together to make sure that did we bring enough people into this testing environment to cover all these bases, because one person isn't doing it all. Occasionally, but not always. An approved agency is necessary, and the building official determines that. Now, I know there are some jurisdictions that actually maintain a list of approved special inspectors. So like I said, it's an interesting question to ask your local authority. And if it's possible, get yourself on that list. So now the next time an inspector is on a job and they don't have someone lined up, maybe they'll call you. Independence shall be objective, competent, and independent. I think that speaks very well for the people in this room. The agency shall disclose to the building official and the registered design professional any conflicts of interest. This is right up our alley, right? This is what we do. We're third-party inspectors. We don't allow ourselves to be influenced. Have to have an approved equipment and periodically calibrated. Approved agency shall employ experienced personnel. So what I'm showing everybody is this is us. Whether we know it or not, this is why we're on the projects. This is why we have our scope of work. This is why we're following the sequences outlined in the drawings, because either singularly or collectively, we become the team that's able to check all the boxes in the building code and the local code officials' requirements. You hope? All right. Okay. All right. So let's talk about our case study project. I was requested to participate at a level on the team to demonstrate systems, right? I was already the tab contractor on site, so my men knew the systems. We were determined to be best outfitted to come up with the ways of challenging the systems and with the knowledge of their operations and interrelations to demonstrate the systems. We didn't work alone. We worked with controls, we worked with fire protection, we worked with electrical, mechanical. It's a team effort, it truly is. Many of you have performed aspects of this testing. This is my whole, this isn't right, you can't do it that way, you don't know what you're talking about. Let's put that all on one slide. And we'll say, actually I did, at that time, for this job, meet everybody's requirements, and everybody was happy, and the building occupied. Are there better ways to do it? Sure, everybody's got a better way. Did 5 more projects come up after that? Yeah, they did. Did they get done? Well, they're occupied. So, but they're not the way you did it. They're not the way you would have done it. You may have been asked to do something differently. Doesn't make any of us wrong. It just shows how many different ways and how many different authorities having jurisdiction there are out there. For coordination, it was the entire construction team. Mechanical, electrical controls, fire protection, and tab. And we wanted everybody present during the actual functional performance testing so that no one trade's activities or failures or faults would cause an entire 15-person testing team to have to stand by idly. The owner and AHJ had direct representation. The DOR and AHJ had already decided on final acceptance testing. That was a case of us submitting and them amending and we resubmitting, and eventually we all came to agreement that this is what we can do and this is how we're going to do it. And then we asked them to be present, because what better way to demonstrate a system than by getting everybody who can sign off on it in the room at the same time. The fire department and fire marshal were there for their input. And every fire department, every fire marshal wants to be involved with high density occupied buildings. They want to know if they ever get that fateful call that there's a hotel on fire, that they already know the building, they have faith in its operation and design, and they have trust that they can get the people out. They want to be involved. And lastly, there's going to be a lot of smoke coming out of the building, which is pretty exciting, and everybody can dial 911, right? So something else to keep in mind. This is a 1,100 room hotel, so obviously a pretty big structure. It had an open atrium. That's the atrium glass ceiling up on the top there that you see. It also had multiple grades below level for an added level of difficulty. This is inside. This is the atrium. We have 16 stories above grade, 6 below, with ballrooms and conference center. 8,000 square feet of lobby and 16 stories tall. Open atrium with skylights. Corridors all open to the atrium. You can see that band of dark with the light on the left-hand edge of the picture. That's each corridor for the hotel rooms that opens out into the atrium, because if you're going to build an atrium like that, you want people to look at it, right? So of course it's an open concept. Created some challenges in the design concept, but those challenges were met. 700 plus smoke control dampers in this building, 30 plus smoke control test modes. The atrium alone, over 2 million cubic feet of air that had to be dealt with. And the atriums had 9 air handling units that we had to get working right, get working together, and at the same time. The fire control sequence, again, this isn't a high-level discussion about all the aspects of fire control. Each and every aspect of some of the things I brought up today can be their own presentation. This is just a higher-level review, and then we're going to talk about some methodology, and then we're going to say, wow, that looks neat, and ask some questions. All right? So to keep it basic, we have a laser-detected smoke activity. We have transfer smoke control doors to open. These are the exterior doors that open to the street. We have smoke exhaust systems for corridors. We have atrium smoke evacuation. We have corridor supply and makeup systems being maintained in operation. Again, this is a whole building approach. All associated air handlers and smoke control damper sequences enabled, and the corridor pass-through smoke control doors released on event. So all the doors that led out to the atrium for the end of the corridor, there's really nowhere to go. It's just a little balcony at the end of each corridor. But each one of those is, of course, a smoke control door. Auto close, electronically held open. You've seen the type. So they all had to be verified to release when we wanted to do the atrium test. Just to put some factors behind the airflow, we had 4 exhaust fans at 100,000 each, 9 air handlers with a total of 90,000 CFM makeup. The transfer smoke control doors from the street were supposed to bring in about 12,000 CFM each. And then miscellaneous intake and opening and louvers for a total of 240,000 makeup air. So we were looking at a net negative of 70,000 CFM for properly operating atrium smoke control. Pictorially, we hope an atrium looks like this. There's a fire, there's a volume of smoke, there's calculations to say how big that volume of smoke should be, about 20% of the overall, unless it's engineered and designed otherwise. And then as you can see in this example, it worked well for the application I had. We had smoke control doors leading to balconies. And in this case, they're demonstrating that they could actually be connected into an evacuation mode. So you want to have 6 feet of clearance. That's the red circle and the arrows. So we're assuming for a design concept, we're going to start with the simplest event. We have an axiometric fire, and a properly designed atrium will hold a volume of smoke above the egress pathways. Design is based on all systems working and all the faults debugged. Now, as you can see, this system's working and there's still smoke in the building, right? We're not removing it all, we're just controlling. We're controlling to that 6 foot exhaust parameter, 6-foot exit parameter. Here we're expanding the design concept a little further, and we're saying, well, what if it happens in one of the outer fringes of the atrium? Will it still work? And we want to try to test and challenge a system to see if we can determine if it will work as properly designed and maintain that 6 feet of egress. That's so important. It's a concept called plug holing. It's an important concept to understand, and you can't test for plug holing without a visual method, right? You can't turn on an exhaust system and go, yeah, that velocity is going to be too strong, it's going to overpower, and what you're going to end up doing is sucking clean air up and out. The goal is to maintain a smoke bubble, for lack of a better word, and you're exhausting air while you're replacing air below it, but you're not trying to disrupt, because if you disrupt, you can have a failure of your smoke control system, as this picture illustrates. In this case, the fan or grill intake velocity is too great, and the clean air is pulled up through the smoke. Results in an overload of the retention volume, and a clear egress path is not maintained in this example. Here's an example where we have lateral current disruption. So when a mechanical engineer and architect are getting together on concepts for large volume smoke control, they want to think about lateral effects. You don't want just a couple of high velocity makeup air grills, even if they're located at the 10 to 12 foot level where they're not blowing on people walking by. It's going to provide disruptive factors. And in this case, the illustration is indicating how you can provide disruption of your rise of your smoke, and now you're scattering it, and now you're losing your ability to reduce that smoke volume in a controlled manner. Egress path has not been maintained. So what do we do? What do we test? How do we do it? We want to know that the airflow and damper configuration to ensure removal of the makeup airflows are achievable. We can do that ahead of time, right? We don't need smoke for that. Tab and commissioning. Lateral airflow current disruptions. We don't know that's a problem until it becomes a problem, but if we recognize during testing or commissioning that we have some really strong lateral discharge devices in the open concept, we're going to want to scratch our head and check into that a little bit. Makeup sources and full automation, fire alarm and commissioning, and overall current architectural interference verification, smoke performance testing, visualization is how we're going to accomplish that. Does this building work? So in our example, for the test parameters, we want to use smoke, and we want to have a fan to boost that smoke into the airstream. We're going to check the patterns in the air currents, trip the lasers, observe the grills and registers, observe the smoke evacuation path, and ensure there's no plug holing. Here's the candles, here's the fan. And I'm going to show you what we did with that fan in a minute here. The candles are just standard over the counter. We use the 3 WCs at the bottom, the big ones. These have a very useful purpose in our industry, whether it be for kitchen test or something like that. The downside is you got to be able to control your smoke. So, for those of you that have old school done this before, it can be challenging sometimes. Select the right candle and control it. We made a burn chamber for it. The bottom of the picture is a expanded metal intake. Then I got a little mouse hole there with some expanded metal as the bottom of it. And I can light a candle, toss it in the mouse hole, and now I'm generating smoke. Well, the smoke's just going to billow up and build, but that's the purpose of the fan on top. So I put an inline fan on top, I put a speed controller on it, I put a blast gate damper on it, and an adjustable elbow. So now with those added features, I can control the amount of smoke, I can blast gate it. I can't stop it once it's started. You got to keep going, but you can control the volume in effect. We made it portable because when you're doing that large of a hotel, you need to be portable. So we welded some brackets on some carts and got ourselves a whole kit together. The burn chamber and fan assembly on the left. On the right-hand side is our heat source. Our heat source is a vertical shop heater, 200,000 BTU shop heater. I took the cap off the top, I sleeved a piece of metal over it, keeping the intakes open, and this provided me heat. Heat is important because I'm trying to simulate a fire without actually lighting a fire in somebody's brand new hotel atrium. All right, and I put it on a piece of plywood, had fire extinguishers nearby. Here are smoke evac intakes. They're perpendicular to the plenum, which isn't an issue, but again, remember we had the glass ceiling. And that's where we wanted to make sure that we could retain enough smoke volume to prevent plug holing. Here's my laser looking down over one of the balconies. The right-hand picture is the repeater, the reflector, the left-hand side, and I think it's about 5 or 6 levels up. Shoots all the way across the atrium, and they had multiples of these around. One of the requests from the owner's rep was, hey, we don't need to challenge everything. In other words, you don't need to pick a spot in the corner and try to prove that we didn't put the lasers in the right spot. Let's make an assumption that we've properly laid out the lasers. We've done our analysis on that. Let's just go ahead and set up near the overhead projection point of the laser, and let's use that as our location. Okay, it's your design. You and the AHJ work it out. I'll do this wherever you want to do it. So we did. We burned 2 W3C double wicks. We were underneath the laser. We have 200,000 BTUs of heat coming up off that stack at the bottom there. And the smoke is simulating an engulfed yet localized fire. When you're standing in the middle of a fully marbled solid surface atrium, what's going to catch on fire? Trash can, sofa, the plant. I mean, there's just nothing there to burn. So the concept wasn't that challenging to say, let's just simulate something right here in the middle, as if a sofa catches on fire and something else, maybe a stack of luggage, who knows. There just wasn't any burnable materials in there to say, okay, this is where a fire is most likely to happen. So they picked a spot, and we entertained the spot, with the goal being to create this environment. We have a true rise heat induced smoke plenum going up, tripping the laser, activating the systems, and challenging the system. It's a little smoky down there at ground level, just due to some backflow out of the fan that you can see there, but for the most effect, you can see that smoke is definitely rising up due to the heat influence of the heater, and the test was deemed successful to challenge the system. We were able to observe the sequences, all the fans worked as they were supposed to, and the atrium was tested and signed off. Questions on that? Okay. Ballroom testing. The ballroom had a lower ceiling, much like this, and the design was for egress height, smoke-free pathway. Smoke was injected with a smoke generator in the fan. We did not need to use heat due to the low ceiling. Smoke was allowed to fill the upper ceiling area. Then the systems were allowed to initiate. We blocked them out until we got enough smoke in there. And then we watched the airflow patterns and currents. Here's a picture of it. The smoke is being formed. The design intent was to keep the exit signs visible, so we filled the volume up, waited till the fire marshal said, okay, that's good enough, let's turn the systems on while you keep adding smoke and let's see what happens. Okay, so looking across the area here, we're seeing a general smoke layer building and dropping, and we're continuing to add smoke until everybody that has an opinion gets to see enough to sign off on what they're seeing. Again, I didn't stipulate how much smoke they wanted. I didn't stipulate what size energy fire we were simulating. They wanted to see their systems in operation. We gave them that opportunity. Any question? That wasn't right. Let's see, 55, let's try that. There we go. Oh, I got lucky. Any questions on the ballroom? Okay, so again, we didn't feel the need to use any heat. Our little booster fan on top of the smoke was enough to just get the smoke up into the plenum instead of it just, falling and laying. Because again, it doesn't have its own heat rise and buoyancy effect that you're looking for that you'll see in a natural fire. Corridor testing. Okay, we're going to wrap up our discussion with corridor testing. They wanted a blackout test. They wanted to simulate what's the most fearful condition in the middle of the night in a hotel. There's a fire. You're tired, you're disorientated, you don't know where the hell you're at. You open up your door and you can't see anything, right? They want to cut that time down. I don't remember the exact time they wanted, but they asked us, black out a corridor. We actually locked out the sensors, smoke detectors. Blanked out a corridor with fog, and then we energized and they timed it to see, because their goal was simulate a corridor blackout and then time how long to recover the space so that people can see again. Time and distance to an exit sign, all right? So the smoke was injected. This time we're using a theatrical fog generator. Much better control over this than lighting a candle. Corridors are a lot harder to manage because the space is more confined. But I'll tell you, this theatrical fog generators work great for it. Smoke detectors were initially covered. The exit sign, line of sight limitability was established to the AHJ and DOR satisfaction. Smoke detectors were then uncovered. 2 detectors were needed to initiate an alarm per zone. Line of sight restoration was timed. Airflow patterns and currents observed. Initiation was always allowed to be via automatic. We weren't ever manually tripping. For equipment, we need a fog generator. We need a high density fog fluid. We used glycol base, leaves no residue. You would not use this for a laser trip because it's not going to trip a laser the same way that the carbon products in smoke will, but it does work just fine with the other style smoke detectors. Here is our unit. We have a remote control for it, and we have plenty of fog. And how much smoke can you generate? That much. You can generate a lot of fog with these things. You can generate that much. Okay? So we were able to give them the blacked out conditions that they were hoping for, and then we were able to time the recovery time of the makeup air exhaust system combined operation to get ourselves clear visibility of the exit signs. Any questions on corridors? Yes?
The line of sight recovery, is that a code standard time sequence?
It was for our jurisdiction. The inspector, I'm sorry, I can't remember what it was, but there was a distance and there was a time. And he stood a distance from the exit sign with his watch, and when he could see the sign again, he was satisfied, and if it met the time requirement.
Does anyone else run into that?
In the 90s in California, how they did it, that's very old.
Mm-hmm.
How to do smoke.
What would you see now? What would you think would be a...
Almost all the smoke control systems, particularly for exhaust, performance-based design, so it's a computer model that's done to do that.
Mm-hmm.
And part of that tab result is really trying to go and verify of all the assumptions they made in the model for airflow, supply, exhaust, kind of whatever, is what's in the field, actually what's performing. So although the actual smoke has its, kind of place, it's very hard to kind of match that exactly to the smoke generated in the fire size that the model assumes.
Right.
So it has its place. You can kind of see movement and kind of whatever, but particularly doing a computer model, you really want the tab results to back check to make sure the model assumptions jive. And if they don't jive, they might actually have to go rerun the model to see how
if it will perform. So by that, you're talking about the air change rates the makeup and exhaust combined with the volume to calculate the change rates.
Well, the newer codes don't have anything with air change rate.
No, they don't. No, it would be the engineer of record for the fire systems.
Yeah. So most of it's computer modeling based, so I advocate for those who have CAD stuff is, trying to figure out what you need, kind of verify. Not only, see it happen, but it's just the velocity that you're not supposed to impact either for supply into atrium, those doors are popped open and, air's coming through from the street. But model assume a velocity across that opening.
Right.
You need to kind of verify, are you, on an average, doing that across the opening. So there's a lot of stuff. As the buildings become more complex and do more performance-based designs, you need the test data to kind of verify it's in line or no, it's not in line. But, kind of, someone might have to rectify, if there are major differences.
Right. Well, I'll be the first to admit the initial point for these tests was very subjective. Once that subjective issue was accepted and set aside, it became objective at that point. So very subjective in how much smoke they wanted, the distance, the time, and those factors. But once they made those decisions, they were able to make an objective analysis of those participating. Did we achieve what we thought we were going to achieve? Now knowing that all the calculations have been done, because this wasn't that long ago, so all the calculations were done, but did they achieve that level of objective observation where they could push the I believe button and go from there? This is a VAV smoke detector, by the way. That's why that picture's up there, because I just love putting that picture up whenever I do a fire life safety presentation. Most of you probably wouldn't put a detector like that on the inlet of a 6-inch VAV, but hey, why not, right? Yes, sir.
Just out of curiosity, kind of there's some jurisdictions or even some owners that kind of want this kind of theatrical smoke testing, kind of what have you. What was the case in your particular instance? Is it something the local authority was saying, like, hey, I want this, or is it the owner, or kind of just curious kind of the driving force behind,
One of the first ones was the owner for his hotel. He says, I'm not letting an occupancy happen, whether the AHJ wants it or not, until my life safety team is satisfied, not with just the numbers, but they wanted to see something. They wanted to be able to make an objective analysis of the system's performance as they related to each other. And then it grew from there. The AHJ liked it so much, he recommended it to some other people, and they got to see it, and that was Washington, D.C. Then Montgomery County was doing a courthouse, and they wanted to see it, and a couple other people. They just wanted that factor of, I can see it. I'm seeing the airstreams. I know I don't have air curtain interruptions. I know I don't have plug holing because I can see it.
We have the same thing in University of Maryland and Baltimore. They wanted to just see it. They just wanted that visualization to say, all these things happen, smoke got dissipated, and they saw it.
It's no different than the second step in the fume hood testing, right? The first one is to set the velocities. Well, why aren't I done? All the velocities are right. Now I got to smoke it. I got to do the smoke candle around it. Why do I do that? I already know it's right. I set the velocities. So trust but verify, I think Reagan used to tell us. All right, any other questions? Yes, sir.
More just anecdotally, so if we work in a jurisdiction, it still requires or requests a smoke control, like the actual smoke demonstrated, however you do it. And just because, like, a lot of times when we do an atrium, you get a CFD model, and it says, yes, your flows have to be between this and that, and the horizontal intrusions. And, a lot of it talks about the wind direction, there should be no nominal increase or ability to remove smoke. The wind comes from this way at this many miles per hour, or this way at this many miles per hour. It's actually really interesting, even though you use the actual smoke, you try to beat it, you try to do whatever you can. It doesn't always work. Via the CFD model, the information that you get doesn't always match because it's a model. And, something might be coming in at half the miles per hour. C&D model says it's perfect. And you're getting all the right velocities, you're getting all the right flows, but rather than going up the atrium, you're just going right in one door, right out the other. You're smoking out the
Yeah.
other.
Yes, the buoyancy factors, which is why we used heat in the atrium, and stack effect are a couple of the bigger factors that you just can't see that on a balance report. You know, and that's why some people want that objective observation. We're at our time. Anybody else? Yes, sir.
So on naturally vented makeup systems, say they use electronically open door actuators to allow air into the atrium.
Yes.
Door monitoring is typically required to prove door openings, but how do you control that lateral velocity if you have doors that fail to open or have been impeded in some fashion? Because I noticed your slide showed that that was the greatest disturbance to the tenable areas. Is that just overall smoke coverage? Is that the density of the smoke? Like, how fast is that filling up all those levels if you have that exceeded lateral velocity, especially when you're having designs that utilize those things that may not always prove open, but you're not going to disable or modulate your preset tab speeds to compensate for a failure of the door actuator?
Yeah, that's a great question. My conversations with the fire systems designer was more along the lines of the way the entry doors were designed and built to open out. I think I said there were 12,000 CFM each. That is the makeup air flow path. So they've already determined that that is going to be the pathway for makeup air. So I don't think they were that concerned on if the velocity jumped from, say, 12,000 CFM a door equivalent to 18,000 CFM per door equivalent. The lateral current issue was around the rest of the perimeter of the atrium and how regular HVAC makeup was introduced into the atrium for temperature control, and to make sure that those velocities weren't going to be of such excess that they could disrupt a smoke model. And again, like he said here, it's all based on smoke modeling, but one of those factors included that inrush of a couple 100,000 CFM air of makeup air from the street. So a variation in that, I think, must have been in their models. Any other questions? All right, thank you, everyone. I appreciate your attendance today.